I'm Nima Parsi from McGill University. I'm working in Professor Demopoulos group. So today I just want to have a quick overview over some part of my PhD work has been done during the past 4 years. So basically what we are doing, we are trying to use the same technique as the previous talk, electrophoretic deposition. In this case, we want to deposit a thin layer of nanotitania to be used as a photoanode in dye-sensitized solar cell. So I'm just going to skip this because you already have heard. But basically, I mean to prepare the conventional method to prepare this nanotitania film to be used as a photoanode is screen printing. As you can see, we make a paste of titanium dioxide, and then we can just doctor blade or screen print it. But alternatively, we are interested in electrophoretic deposition because it's a really fast, facile, and easy to control process, and has a huge potential from industrialization point of view. So basically, as you just heard, I mean, it's a very simple method. I mean, we just have a very well dispersed suspension. We basically charge our particle. We applied an electric field, and our particle moved under this electric field, and they will be deposited on the surface of our substrate. You will be amazed if you hear that about 96% of the world vehicle body are electrophoretically coated. I have like a short movie here. This is a BMW company. As you can see, this is the body of the car. It's just immersed in the EPD or electrophoretic bath. So they basically apply like a voltage for a certain amount of the time, and they electrophoretically coat basically the body of the car. And this thing is known as the e-coating or electrophoretic painting. It's known as this in the industry, and it has been in the industry since maybe 1970. So my PhD was divided into two big parts. The first part was using an aqueous suspension. So basically, we use just water, and we use a P25 particle, which is a commercial type of titanium dioxide particle. And for the second, for this part, we have three main issues. First of all, since we are working in the water, we have the issue of the electrolysis of the water. So basically, we managed to have to work with the voltage below the voltage of the electrolysis of the water. So in this way, we suppress any bubble evolution due to this electrolysis of the water. We did have two other issues, stability of our suspension and the film adhesion, which I'm going to explain a bit later how we address these two issues. And the last part of my work, we decided to move from water to an organic suspension. So basically, we use just isopropanol as a suspension, and we use our home-sensitized titanium dioxide particle. So as some part of my my result, so basically for those two, here is the first part is where we are working with the water. So for solving those two issues that we had, as I mentioned before, first of all, suspension stability, and the second, the adhesion of our film, we have a very simple solution, but maybe not that simple, maybe 4 years ago, but now it's a bit simple. So basically, we use just a zinc nitrate, a very simple inorganic salt. First of all, to charge our titanium dioxide particle by this zinc ion can adsorb on the surface of our particle and charge our particle. And for improving our adhesion, I should explain a bit how this the mechanism of our deposition. So basically, in my case, you can for the EPD you can apply a constant current or a constant voltage. In my case, I apply a constant current, and we decided to probe the voltage profile at the surface of our substrate, which is a cathode here, during the EPD time. So basically, this is the voltage profile versus the deposition time. And as soon as we apply the voltage, there are two reactions which can happen at the surface of our cathode. Reduction of the hydrogen, reduction of the nitrate ion, and as you can see, both of them can produce the hydroxyl group. So basically, we can increase the pH at the surface of our cathode locally, and this has been verified by some other experiment too. So basically, in the first 25 seconds of our experiment, as soon as we apply a voltage, this titanium dioxide particle, which is surrounded by this zinc ion, it starts to move toward our cathode. And when they reach this region with the high pH, this zinc hydroxide will be deposited in the form of zinc hydroxide. And this hydroxide material is very well known as a binder. So in this way, it improves significantly the adhesion of our film. So basically what we are doing, we are coupling the electrolytic deposition of this zinc hydroxide with the electrophoretic deposition of our titanium dioxide particle. And then we verified that when the voltage at the surface of our cathode goes above minus 1.2 volt, this zinc ion will deposit it in the form of zinc metal. But it doesn't matter for us because after our annealing post-treatment at high temperature, all these zinc components were converted to the zinc oxide, and we get a composite of titanium dioxide zinc oxide. This is a cross-section of the film. We still have the problem of this crack formation during the drawing, which we solve it by the multi-layer deposition. But as you can see, we can get a very nice and uniform film. And the zinc, you can see it's uniformly deposited across the film. When you see at our TMA mesh, we see that this zinc component, it's forming kind of a partial shell or like an island type of deposit on the surface of our titanium dioxide. So then we assemble the cell using this composite film and compare it to the bare titanium dioxide, and we see that we significantly improved the open circuit voltage. So we wanted to see what's the origin of that. We did a lot of electrochemical measurement like impedance spectroscopy, open circuit voltage decay. We see that, it seems that the zinc oxide is acting as like a potential blocking layer. This is a schematic of our cell. This is our anode. This is our cathode. Here is the electrolyte. So basically, we know that the photo-injected electron, it can be recombined from this to position. And as soon as we bring this zinc oxide has a bit higher conduction band compared to the titanium dioxide. So basically, it can act as a potential blocking layer. And it's blocked basically the recombination. In this way, it's improved the open circuit voltage. And finally, the efficiency of our cell. The highest efficiency which we got from a film prepared in the water, it was around 6%, which is quite respectable in this area. For the next step of our work, we said, okay, let's go a bit further. Why just zinc nitrate? Let's try other salts like aluminum chloride or magnesium nitrate too. And in this way, we prepared 3 different composites, as you can see, with different quality depending on the quality of the suspension which we prepared these 3 different films. And to just flash back to what has been done so far in the literature, basically they usually use a secondary metal oxide with a high conduction band in addition to the titanium dioxide. In order to suppress the charge recombination, they usually put it as a overcoat on top of the titanium dioxide, or they put it as an underlayer in some cases. But both of this has like some drawbacks. For instance, in this case, it's kind of impede the injection of the electron from the dye to the titanium dioxide, and in this case, impede the electron collection from the titanium dioxide to our F2 glass. But in our case, we have like a total different type of composite. We have, as I mentioned, we have a kind of mixed titanium dioxide zinc oxide, because our zinc oxide were deposited in the form of like some kind of island deposit. But we wanted to like comprehensively study the photoelectrochemical behavior of this structure for these 3 different basically composites that we prepared. And we saw the highest efficiency is still for the titanium dioxide zinc oxide, and it's mostly because in case of magnesium oxide and aluminum oxide, they have way higher conduction band compared to the titanium oxide and zinc oxide. So in this way, according to our impedance spectroscopy result, they resulted in a very high charge transport resistance, or in other words, they cause a lower conductivity in our film. So that's why they resulted in a lower efficiency and lower short circuit current compared to the zinc oxide. And for the last part of my work, as I mentioned before, we basically just switched to the isopropanol instead of the water. But in this case, we didn't even use any kind of inorganic. So it's just pure isopropanol that we use. And we synthesize our own titanium dioxide using a very simple controlled force hydrolysis. So basically, we get 2 different types of particles. On your left, you can see we get a very small anatase particle, around 5 nanometer with a huge surface area. And on the right, you can see we get some kind of sea urchin-like big rotile particle with the particle size around 200 to 400 nanometer, which they can use as a scattering particle in our case. And instead of using this conventional configuration photoanode that we usually have in dye-sensitized solar cell, where we have a thin layer of transparent titanium dioxide, and on top of that, we put a scattering layer, we decided to mix these two particles to each other. So basically, we co-deposit these two particles that we have in order to have a hybrid or, let's say, bifunctional photoanode. To do so, we prepared 3 different suspension with different ratio of anatics to the rotile. Anatics is the smaller particle, rotile is the bigger particle. And you can see from the left to right, when we start to increase the ratio of our bigger particle, big rotile particle, we start to increase the quality of our film, and we have noticed that we are strongly increasing the adhesion of our film. And we get a quite, I mean, we were surprised, I mean, how robust and adhesive was this two film. I have a very short movie. I mean, it's not maybe the best way to show this, but it can give you an idea. This is a film prepared from a 50-50 ratio, 50% anatics, 50% rotile. I just put it under the maximum pressure of the hot water, the water that we have, to just give you an idea how robust this film. And you can see almost nothing to this film happen. But you should keep in mind that this film didn't go through any kind of post-treatment, any kind of high temperature post-treatment or compression, and we didn't use any kind of binder. And basically, we are using just a nanoparticle dispersed inside the isopropanol, and that's all. And we did the deposition at room temperature, maybe less than 10 minutes. And we get this film. And finally, by some optimization from the ratio of the film that we use and adding some kind of a bit of P25 particle, we get an outstanding efficiency around 8.6% efficiency, which outperforms the cell prepared by Dye-sol paste, which is a commercial type of the paste. We are quite happy with this result because, to our knowledge, this is the highest efficiency reported so far for a film prepared by this technique, basically electrophoretic deposition. And as you can see, here is the cross section of the film. There is no crack, and interestingly, we can deposit it on different type of the substrate, like flexible metallic substrate or plastic substrate, and nothing happened to this film, basically. To just summarize, the same as previous talk, I mean, we also use this technique. I mean, I just want to mention how versatile and strong is this technique. We also use the same technique for depositing this colloidal particle, and currently I'm using this technique to fabricate like an anode electrode for the lithium-ion battery. So you can think of many, many different applications using these techniques. And finally, I want to thank my supervisor, Professor Demopoulos, our supporter. This is the demo cell that we have in our department. Basically, it's made by electrophoretic deposition. The size of this cell is something around maybe 20 centimeter by 20 centimeter. And thank you for your attention.